All right, so we're doing the end of the combined gas law. Listen up. Is this the problem that we were on? Is this the one we were doing? Okay, so I know we had gotten most of the way through the setup for this one. So we had labeled this as our V1, this is our P1, this is our T1, and we had to change the temperature to Kelvin because the temperature always has to be in Kelvin, right? This is our V2, and this is our P2, and we're solving for T2, okay? Now, there's a couple of tricks on this one, okay? First trick is you've got to remember to change your temperature to Kelvin, right? Okay, so you always have to watch out for that. It does ask for the temperature in degrees Celsius, but you cannot work a gas law problem. Yeah, you'd have to change it back at the end. Yep, I know, it's kind of tricky. That's one of the other tricks that I was going to get to. You just stole my thunder. Thanks a lot. No, that's fine. So 0.800 ATM, that's P1, times our V1. Now, we've already started it this way, so I'll just keep doing it this way. Really, if I was going to do this over, this is 90 milliliters, right? Your V2, and then your V1 is in liters. So probably the easiest thing to do would be to change this one, the liters, to milliliters by multiplying by 1,000. But since we already did it the other way, we'll just keep it the way that it is. So it's 0.180 liters, I think, is what we had written there, divided by our temperature, which what's our temperature once we add the 273? 302 Kelvin. And that's equal to our pressure. Our new pressure is 3.20 atmospheres times our new volume, which we did dimensional analysis here and figured out this is 0.0900 liters. Okay, divided by our T2. That's what we're actually trying to find. That's what we don't know. Okay. So when we solve this, it's going to give us a temperature in Kelvin, all right, which is not what the question is asking for. It's asking for degrees Celsius. So then you have to subtract 273 at the end, okay? Is everybody okay with solving this, or do we need to go through, like, how you would actually work this out? The reason that you have to use Kelvin for all of these is because when you relate Kelvin to either temperature or pressure, the relationship only works if you're using an absolute temperature scale. In other words, a temperature scale that goes all the way down to 0, okay? So we need a temperature scale when it's at 0, the volume will be 0, okay? It needs to be a direct correlation like that, okay? So that's why we have to use Kelvin. Celsius just doesn't work in the gas law problems. Now with this one, it seems like it would, right? Because 29 degrees Celsius is a positive number. It would make more sense to you that we can't use Celsius if we had a number like negative 34 degrees Celsius, right? Obviously, I can't use that number here because then I'm going to end up getting a negative. If I was solving for pressure or volume here, I would get a negative pressure or a negative volume, and that doesn't make any sense. Or what if I had 0 degrees Celsius as my temperature? I can't put a 0 on the bottom of a fraction, right? That just doesn't work. So we need to do these in Kelvin, okay? All right, so I don't know what the preferred method is here. I think what I'm going to do is just take this entire thing right here, divide it. Or do you guys like the cross multiplication way better? You like that better? Okay, so it's kind of like a choose your own adventure thing here. So we're going to cross multiply. You've got the 0.8 times the 0.18 times the temperature. Okay, you're going to multiply all of this together. Okay, and once you do that, it's going to give you 0.144. I'm going to have to write this up here. 0.144. Don't worry too much about the units. We'll worry about that at the end. That can kind of confuse the issue here. Times T2, right? Because I basically multiplied the 0.8 and the 0.180 together. That gave me 0.144, if I did that right. And then you multiply that by the T2, okay? And that's going to be equal to the cross multiplication of the 302, the 3.20, and the 0.09, okay? So once I do that, yes.
So
I didn't. I posted it this morning because you didn't really need it for a quiz today because we're not taking a quiz. So, yeah. I'm not rounding anything yet, okay? But that's what you get when you cross multiply here. Oh, you didn't? Okay. I may have done that wrong. 302 times 3.2 times 0.09. Nope, that's not right. I don't know what I did there. Okay. This time I'm getting 86.976. Is that better? All right. So then to solve for T2, all you have to do is divide both sides by 0.144. Okay, that will get T2 by itself. Yes? When you take 302 times 3.2 times 0.09, yeah. When you cross multiply, you're basically... There's a couple of different ways you can solve this. We're just doing the cross multiplication method. Okay? All right, so then when you do that, you divide by 0.144. It's going to give you 604. Okay, now let's be careful here. Look at all your numbers that you have here, okay? This is where some of you got, and actually now we can talk about the sig figs on the Boyles Law test, okay? Or quiz, Boyles Law quiz. Notice, if you look up here, the number of sig figs is 2, right? From the 29 degrees Celsius. But what we did is we added 29 plus 273, right? That gave us 302, and we round to the ones place. So now, once we change it to Kelvin, that number has 3 sig figs, okay? So you want to look down here to decide your sig figs, not up here. Okay, I know that's a little tricky. That would apply to yesterday's quiz. So if you missed a point for sig figs, that's probably why. We did talk about it. Yes?
So number 4,
Are you talking about the quiz? I'm not concerned with that right now. So here's your question, okay, or here's your setup. All of these numbers have 3 sig figs. Do you guys see that? Can we agree on that? 0.800, those zeros after the number, after the decimal, are significant, okay? 0.0900, these 3 numbers are significant. So they all have 3 sig figs, all right? Which means the number I'm getting here is 604. That actually is the right number of sig figs, 604 Kelvin. All right? Now, what do I have to do? Subtract 273. That will give me my temperature in Celsius, okay? Minus 273. And we're going to round this, again, to the ones place when we subtract, because these are both significant to the ones place. Is that what you're getting, 331? Okay. So the second temperature here, well, I ran out of room to write anything. Yeah, 331 degrees Celsius. Well, that's a pretty high temperature, isn't it?
Yeah.
So let's check and make sure we're right here. Helium gas at this volume and this pressure. And then what we're doing is we're basically taking this and we are shrinking the volume. And now it's pressurized, okay? Now it's under a much higher pressure. Does it make sense then that the temperature would go up? Okay? Our pressure's higher now. You put a gas under a lot of pressure, you do increase the temperature, okay? In fact, that's how fusion starts in the core of stars, in case you're interested. Basically, you've got all this hydrogen gas that's floating around in the universe, okay? It eventually starts to kind of come together through the force of gravity because they're a little bit attracted to each other. As that hydrogen gas starts to come together, more and more of it starts to pile on top, and the more pressure gets put on the hydrogen that's in the core, the faster those molecules move, the more energy they get. Eventually, those hydrogen atoms start crashing together so hard that they change into helium, and they release a whole bunch of energy, and now you've got a star. So, you know, in case you're interested. So that's the combined gas law. Oh, yeah, it's all right here. 604 Kelvin. Okay, and then here's a learning check. This is an additional practice problem. I'm not going to go over that one on the video because what we need to do now is talk about the combined gas law station on your mini labs. All right, so you need to take out the, sorry, just a second. Take out the crushed can station. I think that was station number 4 on your gas law mini labs, and we're going to talk about that one. Okay. Yeah, okay, let me make sure that there's not something we need to talk about here. Oh, okay, all right. So let's look at this practice problem. I think these were meant to kind of be a summary of all of the stuff we've done so far. Remember what I said yesterday, okay? This is the only law you need to remember. So I'm glad you asked this question, actually. So we've got a volume here, right? So we could call this maybe a V1. We've got a temperature, so this is a T1. We've got another another temperature, T2, and they're asking for the new volume, so that's our V2. All right? Now, to solve for this, and I'm not actually going to go through and solve this one, but I just want to talk about this conceptually for a second. I don't have any pressures in here, right? So what can we assume about pressure? Well, it's not that it's not there, right? We can assume that it doesn't change, right? It's staying the same the whole time. So just scratch that out. V1 over T1 equals V2 over T2. See how that works? Yeah. So as long as you remember P1 V1 over T1 equals T2 V2 over T2, you can solve any of these problems that we've talked about so far. Okay? You just would leave out a variable if there's something that doesn't change in the problem. Okay? And that's why you cross multiply on this one too. That's why I strongly recommend labeling your variables like I do here, because then you can see, okay, in this problem I've got a V1, I've got a T1, I've got a T2, and a V2. Well, where's the P's, right? They're not here, so just scratch them out. Okay? All right, so there's the combined gas law.